Welcome to today's video. This is the first video in a series of 2 videos where we will deal with cosmology in general relativity. Now, what we're going to do in this video is to start from the cosmological principle, which is the postulation that there should be isotropy and homogeneity in the universe. So there's no spatial point and there's no spatial direction, no spatial direction. Now, this principle, and only from that principle, we will be able to go from the most general possible form of a metric to the Lemaitre-Friedmann-Robertson-Walker metric. In this video, we will do that, and in the next video, we will use that metric that we found to go to Einstein equations and then try to solve them for what is going to be the future of the universe. And then we will analyze a little bit concepts like dark energy and how the content of matter affects that destiny of the universe, but it's not to a great detail, just an introduction, because I know that there are specific courses that you will take later on that will get more in depth. But at the very least, I do hope that this serves as a solid first introduction. All right, let's get to it. Cosmology. We're going to derive the most popular model for cosmology, the initial one, which is the Lemaitre-Friedmann-Robertson-Walker spacetime, and also the dynamics of that spacetime, the Friedmann equations. And we're going to talk about many things related to cosmology. So we're going to derive that from scratch. We're going to derive it from the cosmological principle. We are not special, nobody is. All the points in space should be the same. We have homogeneity. Second part, there are no favorite directions. There shouldn't be any direction in space that is singled out, at least for some observers, right? I mean, obviously, if I have some observer that sees everything isotropic, and then I start moving with some spatial velocity with respect to those observers, well, I privilege a velocity. But you say, okay, there are at least some observers that are not going to see any favorite directions. Their universe, in a way, is isotropic for at least some families of observers. Cool. So those two principles, homogeneity and isotropy, are what we call the cosmological principle. And we can derive what kind of universe we live in if we demand these two things, that the universe doesn't have special places and that no special directions. So let's start from the very scratch, which is saying, okay, this is the line element. I'm going to be saying the metric a lot, okay? So the line element, the metric, I write the most general possible one. If you say I have all the coefficients, G00, this one, I have G0i here, and I have Gij contracted with all the possible combinations. So here we have a metric tensor that has all the components non-zero. It's definitely non-diagonal. I will use this to highlight some, in the calculations, the places where having a non-diagonal metric actually messes with you. All right, so we have the most general possible metric, and we're going to start making restrictions on this metric based on these two postulates, if you want. Homogeneity and isotropy. And let's begin with isotropy. We're going to impose isotropy at different levels. The first level is saying, okay, imposing isotropy for observers of proper coordinates t prime xi. So t prime xi is the coordinate that I use to write this line element, and the components of the metric tensor are functions of t prime and xi. So they depend on time and space. It's a very general metric. It's the most general possible. So prove that imposing isotropy for these observers, and those observers are the ones, because they have as proper coordinates t prime xi, they move in the direction of partial t prime, okay? Then show that implies that G0i is equal to 0. All right, so this is something that we need to think about geometrically. Maybe you should pause the video and perhaps think of an argument why it should be true. Did you do it? Okay, so let's now see my solution and we compare. Now, first of all, let's find the force velocity for these observers, shall we? Now, again, remember that I always tell you that when you take a frame that is proper to somebody, that person is going to be moving only in the time direction in that frame. So yeah, definitely the force velocity will be proportional to partial t prime. But it may not be 1, 0, 0, 0. It will be 1, 0, 0, 0 only if it's in a region of space-time where the particular component G00 would be 1. Otherwise, it's not. And let's see it. So let's call u mu the force velocity, right? And then I know that u mu, the force velocity for those observers, is going to be some component u0 and nothing else, because it's proportional to partial t prime, and partial t prime is the 1, 0, 0, 0 vector. All right, but why don't I write a 1 here rather than a u0? Well, because we know that the normalization of the forward velocity has to be 1, minus 1, sorry, it's a time-like vector. And that means that g mu nu u nu is equal to minus 1. All right, there's only 0, 0 components. So that means that g0, 0, u0, u0, it's equal to minus 1. And what does that say? Well, that says that u0 squared, it's equal to minus 1 divided by g0, 0. All right, so we get finally that u0 is equal to 1 over the square root of minus g0, 0. Okay, and this is the value of the 0th component. And g0, 0 is going to be a positive number because of the signature of the metric. So, indeed, this thing is well defined. So, knowing that, I know now that u mu is equal to 1 over root of minus g0, 0, 0, 0, 0. All right, wonderful. Now that that's clarified, you know, this little non-triviality that we haven't had a chance to address until right now in this exercise, because in most cases we were considering for velocities either in space-time where this coefficient was 1, or in space-time where this coefficient was 1 in a region that we were looking at. All right, so now what we have here is that we need to prove that imposing isotropy on those observers implies that these components are 0. And here's the geometric argument that we're going to see. So imagine that I define the place of simultaneity, if you want. It's related to the notion of foliation of spacetime, but let's just not introduce things that are more advanced than what we're going to see. In the place of simultaneity of this, imagine at constant t prime, there is a spatial surface, right? Let me call it like this, right? So this is a spatial surface that is the constant value of t prime gives you a spatial surface, let's call it sigma. Now, if the universe is isotropic, the person that moves with for velocity u, that for velocity, right? The person that moves with that for velocity may have a projection on the spatial subspace given by constant t prime. So the spatial sections, if you want. Now, this projection, let's call it this projection. Maybe I'll do the arrow a little bit more up to show that it's a projection, right? Now, this projection here, it's singling out a direction in space. So we need to definitely need to demand that the projection of u, the for velocity of those observers, on the spatial sections do not single out any direction. So the projection has to be 0. Again, if the for velocity has some projection on the spatial subspaces in the spatial sections of the spacetime, the privileged direction for those observers would be the projection in space of the for velocity. There cannot be any privileged direction, so nothing about these observers should single out a direction in space. All right. So we need to demand that u projection, so inner product on v, is equal to 0 for all v in sigma. All right. So we can write the most general vector v in components. The most general vector v in components that is in that surface is going to be of the form 0, v1, v2, v3. All right, and then a mistake that people have made, because this exercise was actually an assignment the first year I taught GR. Some people made the following mistake. Oh, right, this is already orthogonal, right? Because 0 times 0, and then all the others are 0. Well, no, that's the point. The inner product is not the Cartesian inner product. The inner product, as you know, is u dot v, it's equal to g mu nu, u mu, v nu. And if we expand this product, we get g0, 0, u0, v0, plus goi, u0, vi, plus gi0, ui, v0, plus gij, ui, vj. Okay? Now, things that we know. Okay, we know that this one's going to be 0 because v0 is 0. Cool, so this is 0. This one's also going to be 0 because v0 is 0. All right. This one is going to be 0 because ui, the ui components are all 0 for u. So this is 0. So all that is left is this term. So we need to impose this has to be equal to 0 for, again, for velocity, not to have any projection on the spatial sections of constant t prime. And then what it means is the condition that we get out of that is that g0i, u0 vi has to be equal to 0. So we know u0 cannot be 0. Remember, this is a time-like vector. Has to have one non-zero component at least. And we know also that this has to be true for all vi in sigma. Now, then what does that mean? So the only possibility is that g0i is equal to 0. And therefore, we have proven what we wanted to prove. We proved that this term cancels. So imposing isotropy in the most general metric, we have that this term has to cancel. Because imposing isotropy, let me remind you, is that for at least a family of observers that are here called the observers that move with coordinates t prime xi, there's no privileged direction in space. And imposing that alone is, and in particular the manifestation that the for velocity of those observers cannot have a projection on the spatial sections of constant time, then we found that the GOI has to be 0. Wonderful. Okay, but there's more that we can get out of isotropy. Let's take the next step. That's called a step. That's called a step. And I follow with the next. Alright, now next step. Let's show that imposing that the spatial components of the acceleration of these observers that will see the universe as an isotropic thing. And look at what I call the acceleration here. This is the covariant derivative of the for velocity in the direction of the for velocity. If we were a geodesic, this would be 0. So maybe they are geodesic or not, I don't know about that. But imposing that the spatial components are 0, so I'm not imposing they are geodesic. Maybe that will come as an intended consequence, perhaps. But I'm not imposing it. I'm imposing that the spatial components of this acceleration vector are 0. So that is telling me that I'm not accelerated in space, because if I am, the acceleration also singles out some direction in space. So I shouldn't have any spatial components of that acceleration vector. All right. So imposing that they're 0 implies that g00 is not going to be a function of the spatial coordinates, and therefore can only depend on t prime. Then after having shown that, show that defining a new frame t xi instead of t prime, this is what we will call the comoving frame, where the new time coordinate is defined as this integral, this is a dummy variable tau, of g00, and of course g00 only depends on this time parameter. We can rewrite the line element as ds squared minus dt squared plus the spatial part. And this is kind of nice, because it's telling me basically that I can write this as a 1 in a particular set of coordinates. Alright, well, let's get to it. First of all, we need to write what this is. Let's write it here. Alright, so I write the spatial components of this for vector here. And you can tell that if I write the spatial components, it would be, I write an I. Remember that the Roman indices go from 1 to 3 at the spatial component ones. So we get that this would be the covariant derivative of the for velocity, but taking this as the spatial components and contracted with the for velocity. But because the for velocity that I wrote here for these observers only have a u0 component, those spatial components, in this sum, I can just write the u0 component. Now, caution! This is a mistake that many people make, and it's very important, and it's related with having more practice with index notation here. Many people would say, oh, but ui is equal to 0, therefore this is 0, so this is already 0. That mistake people make. And the notation may be inducing you, if you're not very practiced with this notation, it may be inducing you to think that. But remember that this is a covariant derivative. This is an affine connection, not a linear connection. Let me show you what I mean. This thing is signifying the components. This is the 0i component of the tensor that is the covariant derivative of the vector u, the 0i component. And remember that there's a part that is linear, that is a partial derivative, but there's another that goes with the Christoffel symbols. Now, if we write what this is, if you remember, there is one part, the covariant derivative, there's one part that goes with the partial derivative, and certainly this is 0 because ui is 0, but the part that goes with the Christoffel symbol, contract the affine part of it, kind of a good pun anyway. The part that goes with the Christoffel symbol is contracted with the full 4 vector. So true, because the ui's are zeros, then this contraction reduces to just the 0th component, but you see how they mix the component. So no, this is not something acting on the 0 vector. This is something acting on the vector component 0y. All right? Very important not to make that mistake. That's why I wrote caution with big letters. All right, so we have that, and we need to compute this Christoffel symbol. So if we write it, if we keep expanding this, we have u0, and u0 here. So we have u0 squared. So let's just write u0 squared. This is 1 or minus 1 over g0, 0. You know, remember that this thing is u0 squared, right? Then the Christoffel symbol, I0, 0. And this is the special component of the acceleration with the index up. All right, we need to compute this object. And compute the Christoffel symbol is something that we know from our differential geometry as well. So let's do it. So we have here the Christoffel symbol, and I use the expression we derived for it in the differential geometry section. Only I particularized for the index I here and the 0, 0. Now, first step, realize that these two things are equal. Why? Well, this is only equal in our particular case. In general, they wouldn't be equal. But they're equal because we have, when mu is 0, we have the component I0. And we already proved that our metric doesn't have a component I0, because that's what we proved in the previous part. So that means that the summand that has a 0 in here is not present. Okay, cool. So I can write Gij. Remember, I and j go from 1 to 3. And then I get this expression. All right. Now, this one is 0. And this one is also 0. And the reason again is the same, that there's no 0j or j0 components in the metric. Components mixed in space and time. So all that I'm left with is this thing. So the Christoffel symbol is going to be equal to minus, this minus here, minus 1 over 2. And then I have Gij, partial j, g0, 0. And I can substitute in here to get the minus and the minus cancel. So I get 1 over 2 g0, 0, Gij, partial j, g0, 0. And this is, again, let me repeat, is the acceleration vector spatial components. All right, so now to demand that they're 0, I'm going to do something. I'm going to lower the index. Why? Because I want to get rid of this. Now, lowering the index here, again, trips people. Probably they will be tripped and do it right by chance in this case. But let's see what I do, because many people think, oh, right, but then II would be equal to Gij Aj, right? That's what it would be. Not quite. In general, definitely no. Remember that A mu is equal to G mu nu A nu, right? If I expand this, I'm going to have the mu 0 A0 plus G mu, let's call it I AI, right? Or maybe J, I should call it J perhaps, to make easier the comparison. All right. Now, of course, if I want the spatial components, then that would be AI, and AI would be equal to G I0 A0 plus G IJ AJ. So you see that this is not true, because you're missing this term. In general, if the metric is not diagonal, even when you lower the spatial components, the time component of the vector with the index up is going to contribute. So it's not true that you can factor things. People are used to that because most metrics that you've been working with are diagonal so far. Well, they might not be. Now, in this particular case, we know that these elements are 0 because we proved it in the previous part. So in this particular case, fine, you're right. You can substitute something with an index down with this. So we can certainly do this. We can find that A, let's say sub j, it's equal to G Ji A super I, for sure. It is true in this case. But remember that it is not true in general, okay? All right, so let's apply that. And in order not to have to change a lot of indices, let me relabel that index K, A sub K. All right? Now, if we do that, we expand this. This is going to be equal to 1 over 2 G0, 0. And then I get G Ki, G Ij, partial J, G0, 0. Now, again, another time careful. You are probably, or some of you would be probably tempted to write this as the delta Kj. Well, in general, that's not true. But in this particular case, it is. Because the metric here we proved, so if I write the metric as a matrix, and I have here the G0, 0, and then this will be the G0i and the Gi0, we know that these are 0, 0, 0, 0, 0, 0, and here you have the matrix made out of the Ij. So of course, if I write the inverse matrix to this, that's going to be with a -1 and a -1. So certainly in this case, the spatial part of the inverse metric tensor is going to be the inverse of the spatial part of the metric tensor. But in general, that would not be the case, because if this were not zero, this wouldn't be a block matrix like this. And in general, this would not be true, that the inverse, you can compute it by the inverse of these blocks. So, all right. But in this case, we can do it. In this case, this is true. So we get that A sub k is equal to 1 over 2 G00. And then I get the delta kj, but I use the delta to change the index j by the k1. So that gives me here partial k G00. Very nice. So let's now impose in this form with the index down, which is much easier. Let's now impose that this is 0, the spatial components are 0. If we impose that, then we get that this has to be equal to 0, and that means that, what should I write it? Yeah, maybe I'll write it here again. All right, so we have that demanding the kth component to be 0, imposing that the kth component of A has to be 0, means that the partial derivative of the metric with respect to that coordinate, the kth coordinate is 0. And because all of them have to be true, that can only mean that G00 does not depend on xi, because all the partial derivatives with respect to xi, x1, x2, x3 are 0. All right, wonderful. So we proved what we wanted to prove in the first part of this part of exercise. All right, so recapping, demanding that the spatial components of the acceleration of these observers are 0. Then we found that, demanding that because that's isotropy, right? The spatial components of the acceleration of those observers cannot exist, cannot point to a direction in space. So demanding that they are 0, we found that the G00 component of the metric cannot depend on xi. It will only be a function of t prime, cannot depend on space, on the spatial coordinates. All right, let's go with the second part. The second part of this part is really easy, because just getting the definition, we get that differentiating on both sides, we get that dt is square root of minus G00 t prime dt prime, okay? And of course, that means that dt prime is equal to 1 over the square root of that. And that means that dt prime square is minus 1 over G00 dt square. We just substitute dt prime by the expression in terms of dt square for this new coordinate, and we obtain the metric that we wanted. This is what we wanted. And now we work with the comoving frame, and the comoving frame being txi. All right, so we took one more step. We got rid of the coefficient G00. This is a 1. All right, wonderful. Now that we tackled this imposing isotropy, we need to start gaining information about what's going on in the spatial part. Let's get to it. All right, before delving into the next part, let's just realize that now this coefficient is minus 1. The G00 now in this new coordinate system Tx, this comoving coordinates, is minus 1. Which means that the for velocity has the very familiar form 1, 0, 0, 0, which is pretty cool. All right, now let's impose another condition for isotropy, which is the isotropy of the local expansion. So what I do is I'm going to define this function h here that I will call the Hubble parameter, or I prefer actually to call it Hubble function. All right. So we have the Hubble function. The Hubble function is, well, let's take a spatial vector S mu. This spatial vector is purely spatial. If it's purely spatial, it means that it's orthogonal to this guy now that we don't have I0 components. So it's got only spatial components. Now consider the following function, which is the Hubble function, and I define it as, if you see, we have the gradient of the for velocity, and this will be representing the spatial components of the gradient of the for velocity. So that is the gradient of the for velocity, and we need to show that imposing that this Hubble function cannot depend on the direction of the S mu. So the spatial components of the gradient of the for velocity cannot depend on the direction, or else there would be information about direction in the gradient of the for velocity of comoving observers. So imposing this, we need to prove that that implies that the derivative with respect to t of gij is proportional to gij. And therefore, h can only depend on t. And also show that partial t of gij is equal to twice the Hubble parameter, if you want, Gij. Then show that defining an a of t equals to the exponential of the integral of the Hubble parameter with respect to time, then the metric can be written as this form. It would be great because this means, look at that, it means that the only time dependence of the spatial, what that would be saying is that the time dependence of the spatial part of the metric is just a scale factor. So the universe is expanding or contracting in time, but it doesn't, the shape will not change in time. It's just a scale factor, a conformal factor for the spatial metric. All right. Where gamma ij is a function of only space and represents the static three-dimensional metric, so it doesn't change in time, of the spatial submanifold orthogonal to the comoving time. Partial t, the comoving time is the time of the comoving observers in the comoving frame. All right, so let's get to it because this is a long exercise. All right, so we get the Hubble function here, that's the definition. Let's say of the things that we need to realize to understand all these steps. Now, first thing to realize, S mu is purely spatial. So S0 is 0, and then there's only S1, S2, S3 components. So the sum over mu nu could be a sum over ij, only going from 1 to 3. All right, that reduces this to Latin indices now. Good. Second thing to realize, don't, the same as before, don't make the mistake of thinking, oh, uj is 0, right? Because uj is this guy's here, so that's 0. True, but this is not the covariant derivative of uj. This is the component ij of the covariant derivative of u. This is what this is, right? So don't make that mistake of saying this is 0 and the whole thing is 0, please. Now, if we do that, we write the covariant derivative instead of the Christoffel symbol as a function of the Christoffel symbols. Then we realize that certainly uj is 0, therefore this term is 0. But this term sums over all the components. And in fact, one thing that may come to mind, shouldn't I have contracted the first index instead of the second? Yes, that's right. I should have written this. But it doesn't matter. This is the Levi-Civita connection, and we're in a coordinate basis. These things are symmetric. So we have I sigma, and we are fine. Now, this is a sum of all the components, but only the 0th component is non-zero here. So we can just write, instead of sigma, we can write a 0 here. There we go. And then u0, we know is 1. So the final result that we get is minus SISJ Christoffel JI0. All right, so that's what we need to calculate to evaluate this, and we can do it. Okay, so we compute this Christoffel from the expression from the Christoffel symbol. Now, we can simplify a lot. We realize, all right, this is the component sigma, the component partial derivative with respect to the spatial coordinates of G0 sigma, sum over sigma. The 0, 0, 1, we know is 1, so the derivative of that one is 0. What about the spatial ones? Well, the spatial ones is 0i. The components 0i of the metric are also 0. So all the elements in this sum give me a 0. Nice. What about this one? This is the time derivative of the I sigma. Well, this one may not be 0. So let's check this one first. This is the I0 components. We know already that those are 0 from the part A, right? Okay, what about these ones then now? Well, these sums of from sigma going to 0 to 4. From 0 to 4. Now, for 0, we know it would be 0. The 0 component does not contribute because, again, I have the I0 component, which I know is 0. So all that survives is the spatial part of this sum here. So literally, this expression here, what I have. All right, so we determine the Christoffel symbol. That means that we have the Hubble function over there. Like that. All right, so to cancel this is really important now, what we have. We have the Hubble function here. That certainly, as I see, in general, looks like it's going to depend on the direction of S. Because in fact, I have some tensor here. I wrote the t instead of the 0 to make it explicit that this is derivative with respect to t. And we have, this is a tensor. Well, this is some tensorial kind of quantity, or in so we have this tensor here, and it's contracted with SI, SK. Now, in general, if I get a random tensor and I contract it with SI, SK, it will definitely depend on the direction of S. I need to find what tensors. This can be, if I want this not to depend on the direction of S, I need to, that actually determines what is the time derivative of the metric, or the spatial part of the metric, because it cannot be anything. It should be something such that when contracted with two copies of the S vector, the result cannot depend on the direction of S. And that has to be true for all S, all special S's, no matter what, no matter which ones. There is only one tensor that when contracted with two copies of the spatial vector S mu gives me something that does not depend on the direction of S mu. And you know what it is? That is the metric, because it gives me the norm of the vector. And it's true for all vectors, for all special vectors. So that means now for this
not to depend on the direction of S,
the spatial direction of S, then we have that partial t, gik, has to be proportional, which is basically what it tells you to prove, has to be proportional to gik. And then we prove the first thing that the exercise asked me to prove. So demanding that this function doesn't depend on the direction of S, I know that the partial derivative with respect to t of gik has to be proportional to ik. Very nice. All right, so let's take another step. Okay, so now we actually have to use homogeneity for the first time in the exercise. I know that the derivative with respect to t of the metric is proportional to the metric, but of course this proportionality factor may be different at each point of spacetime. Now, using homogeneity, this factor cannot depend on the point because there's no spatial point in this spacetime. So this thing has to be exclusively a function of time. Now, if it is exclusively a function of time, I get this expression, and I substitute it in here in the Hubble function. If I substitute in the Hubble function, I get the metric contracted with these two vectors. And these two vectors, right, when I get the metric contrasted with these two vectors, gives me the norm of the vectors. And the norm of the vector is 1. So that's a factor 1. The only thing that survives is the IT. And I get that the Hubble function happens to be a function of only t. In particular, is 1/2 of this IT, where I of t is the proportionality factor that relates the derivative with respect to t of the metric with the metric itself. So, very importantly, I use homogeneity. The proportionality factor cannot make any point special, so it cannot depend on any spatial point. When we have that now, we have proven that this equation here, because if I substitute, we have proven that h can only depend on t, but now I can go back to this expression and substitute h, or actually substitute I by twice h. So that means that partial t gik it's equal to twice the Hubble function gik. Wonderful. So we have proven that one now. That's nice. And finally, we need to prove that defining this thing, the metric can be written as follows. All right, that is kind of cool because you know what this is? This is a differential equation, and an easy one at that. We have one function of t here equals to some function of t and the function that is the unknown. Let's solve this differential equation. Do you know what function is equal to itself times some factor? It's gonna be an exponential. For the last part, what I'm gonna do is I'm gonna rewrite the spatial part of the metric as an ansatz in that form that I'm asked to prove that it is actually the form, and we're gonna plug in the answer into the differential equation to see if we can find a solution of that form. Now, so if I find one, by the way, it will be the correct one because we have uniqueness theorems that tells us. So I write the metric as the spatial metric gamma here that depends on space, and a factor a squared that depends only on time. All right, I substitute in this differential equation, and I get gamma ij, then twice a of t, a dot of t, where a dot is a derivative, equals, and then the right-hand side, 2ht, and then gik, I write the gamma here, and I write the a squared. All right, now, the component ij of the metric will cancel, the 2at would cancel the square here, and of course the 2 is not there either, that 2 goes with that 2. So the equation that I get in the end is that a dot of t divided by a of t, it's equal to the Hubble function. And that's a very neat differential equation. We can integrate on both sides, and here I would get a logarithm, here I would get the integral of this, so let's just write it. So we get here the log of a of t, right? And then this is equal to the integral of ht dt, right? and then I take exponentials to undo, and let me just do it. Wah! Exponential taken, exponential of integral dt h of t, and proven. The scaling factor is what I was asked to prove. The integral, of course, this is an integral some variable t, right, if you want. So it's the antiderivative of h of t. All right, so we check that answer satisfied the equation. So rewriting the metric like this, I can satisfy that condition that I was asked to satisfy, and therefore we found actually not only that, substituting in the metric, the answer, the expression for the metric, we found the value of the scaling factor as the exponential of the Hubble function. That would be something like Hubble, if it were a constant, like a Hubble constant, it would be the Hubble constant times t. But it's not a constant. All right, wonderful. So this part is done. Let's continue, let's gather what we know, and let's continue to the final part to finally determine as much as we can the spatial part of the metric. All right, we got to the final part of this exercise. So the question says the following. Use that a Riemann manifold is maximally symmetric if and only if the Riemann tensor is this function of the metric, where n is the dimension of the manifold. Now, this is something that I'm not giving you a proof for, I'm giving you as a help. If you wanna, it's a long proof. If you wanna see a proof, you can check on Weinberg's General Relativity book, chapter 13.2, and you'll see a proof of that. It's also elsewhere, but in that place, I mean, you have it there in Weinberg's. All right, so use this. I'm giving you that. A maximally symmetric manifold has this Riemann tensor, and also, if a manifold has this Riemann tensor, then it's maximally symmetric. That's what I'm giving you as help. N is the dimension of the manifold. Then use that to prove that the Ricci tensor of the spatial submanifold is proportional to the metric, and that the most general form of the spatial metric is this one. And then we'll discuss about this parameter. This is a k. Okay, this is a k. All right, so prove that. So the first step that we're gonna do is actually compute in general, without assuming we're talking about this metric that I updated already here. Without assuming that I'm talking about my exercise, in general, I'm gonna compute the Ricci tensor for a maximally symmetric manifold. The help tells me this. So what I need to do, well, it doesn't tell me that, it tells me this. So I raise the index to get one index up, and then being able to compute the trace. So I raise the index, and that's multiplied by the metric, and raising the metric is symmetric, so I can flip it, of course. So this thing is a matrix product, and this thing is a matrix product, so it's a delta and a delta. All right. Now that I have the Riemann tensor with one index up, all that I have to do to compute the Ricci is to sum over the first and the third indices. When I replace the index mu by a kappa, I get this sum. This sum is a sum with a delta, so it just replaces the index kappa by a nu. That's what I get here. And here I have the trace of the delta. Now, mistake that people make sometimes. People say, oh, this is 1. It is not 1. This is the sum. This is delta of 1, 1, plus delta of 2, 2, plus delta of 3, 3, and so on. So this thing is n, is the number of dimensions in the manifold, is the trace of the identity, is the trace of the delta. All right, so I have here, now I have the Ricci scalar. This R is the Ricci scalar. I have the Ricci scalar, n minus 1, and then I have the metric that I can take as common factor, g sigma nu, and that multiplies n minus 1. This cancels that, and I have proven that the Ricci tensor, in this case, in general, for this kind of manifolds, is the Ricci scalar divided by n multiplied by the metric. So that's nice. I proved, the one thing that I proved is that if I am in a maximally symmetric Riemannian manifold, then the Ricci tensor is proportional to the metric, and the proportionality constant is the Ricci scalar. That makes sense, because what are the maximally symmetric manifolds? Maximally symmetric manifolds has as many symmetries as you can have. And that means that those are manifolds of constant curvature. Like flat, for example, you have all the rotations and translations, right? Those are all the symmetries you can have. And also, you have, for example, a spherical manifold, something with positive curvature, or a hyperbolic manifold, something with constant negative curvature. Those are maximally symmetric manifolds. You can have they do have all the possible symmetries they can have. A flat manifold, a spherical manifold, or a hyperbolic manifold, they all have all the possible symmetries. So constant curvature. If you have constant curvature, you have symmetry of translations on all the possible directions you can have. And also rotations, the corresponding rotations for the manifold. All right, so we proved it that the Ricci tensor of a maximally symmetric Riemannian manifold is proportional to the metric. Now we need to argue to actually prove what they ask us, which is that the Ricci tensor of the spatial submanifold is proportional to the metric of the submanifold. Then we need to give an argument as to why this spatial submanifold should be maximally symmetric, should have all the symmetries. And then we think, all right, what are the possible symmetries that you can have? Well, all the rotations and all the translations. Oh, nice. All the translations, homogeneity. All the rotations, isotropy. So you need to be invariant on the translation and rotations to satisfy homogeneity and isotropy. And therefore, we conclude that the spatial submanifold in here is maximally symmetric. Not the full spacetime. The full spacetime is not maximally symmetric, but the spatial submanifold, because isotropy and homogeneity, certainly the spatial submanifold is maximally symmetric. And that means that the Ricci, let's call the Ricci Rij for the spatial manifold. Again, these indices are not spacetime indices, are generic indices. I'm considering a Riemannian manifold of any dimension, okay? It could be a spacetime, but I'm not considering a spacetime. I'm considering an arbitrary manifold. Now I'm going to particularize to the spatial submanifold. So this is not the spatial components of the Ricci tensor of the full spacetime. No, I'm considering now the three-dimensional submanifold that is the spatial part of this. And this is maybe I should call it with an S here, the spatial part Ricci tensor is equal to, then we have the Ricci scalar for that manifold. I don't know what is the curvature of that manifold. It will have some curvature, constant curvature, but it could be flat, zero curvature, and then the whole tensor will be zero, or it could have some positive or negative curvature, right? Now, this is R divided by the dimensions of the submanifold, which is 3, and then the metric, which is Ij, directly. And this definitely proves it. This together with the argument that I gave proves it. This would be the Ricci scalar for the spatial manifold. This is interesting because even if the spatial sections are flat, the spacetime will not be flat. And that is actually very important, and we'll discuss it in the next video when we solve Friedmann equations, when we get Friedmann equations. But this is something important because it's a misconception when people talk about cosmology. It looks like our spacetime is flat. Not true. It looks like the cosmological observations we have are compatible with flat spatial sections, but not flat spacetime. Okay? It's different. I want it to be very clear. It's different when I talk about the full spacetime or the spatial sections. It's not true that if the spatial sections are flat, there is no curvature in the spacetime because there could be curvature in the time and space directions. All right. Okay. So that's the first part. We already proved that. And now we need to prove that the most general form for the spatial metric is this one, or the line element rather, for the spatial line element. Let's get to it. All right, so the first thing we do is let me express the Ricci tensor as proportional to the metric instead of in terms of the Ricci scalar. Let me express it divided by 3. Let me call this 2k, the parameter 2k, all right? Just a choice. I don't have to. I could have continued with R, and in the end I could have adjusted, but let me just call it k, because this is a typical way which is expressed. So I just call it that. This is the proportionality parameter, and 2k is equal to the Ricci scalar divided by 3. Wonderful. Now, the nice thing, though, is that this is a differential equation on the metric coefficients, right? Because the Ricci tensor contains derivatives of the metric, and indeed, we know that the Christoffel symbol contains derivatives of the metric. This is the spatial Christoffel symbol, and the Ricci tensor is made out of Christoffel symbols. And you see here, this thing here that's the expression of the Ricci tensor component 1,1 in terms of the Christoffels. Now, important step, spatial isotropy means that I can certainly, I have rotational invariance in my metric, so I can write it instead of these Cartesian-like coordinates, I can write it in spherical coordinates. And in spherical coordinates, the angular part, remember that this d omega squared is r squared d theta squared plus r squared sine theta d phi square, that bit cannot change, cannot be touched other than the r that I have here. So the only possible coefficient that can vary is the radial one, and because otherwise I don't have rotational invariance, and it has to change by a function that is only a function of the radius. Now, why do I express as an exponential? Well, because this thing, I don't want it to change signature. It's a spatial metric. The signature is plus, 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 plus. So that reflects that this coefficient will always be positive. Why do I put a 2 there? It's convenient. I don't have to, it's just convenient. All right. So now, if I compute the component 1, 1, it's the only one I need for this. I just want one equation to determine this coefficient. If I compute the component 1, 1 of the Ricci tensor, is this one here. I substitute the Christoffels. To compute the Christoffel, I need to use the metric. All those relatively long calculations I will leave for you, because there's no point in doing the arithmetics here that at that level. I will leave for you to practice. You can also use the worksheet that I have on my website, but you can also compute it by hand, and computing by hand at least once is not bad. With a 3-dimensional manifold is not that bad, okay? It's actually not too bad. If you compute the component 1, 1, it's just long. If you compute the component 1, 1 of the Ricci tensor, you get 2 over r partial r beta r, where beta is this function here. All right, and we also know that r11, because of this, is 2k exponential of 2br. And there you go. We equate the two things, and we obtain that 1 over r partial r beta r, it's equal to k exponential of 2 beta r. All right, and this is a differential equation on beta that we can solve, and the solution is, now with this solution to this differential equation, I can plug it in again into the metric coefficients that I have here, and what I end up is with this spatial, this is the spatial line element. Now this is actually what I wanted to prove, but let's just write the full metric, because what we obtain is the most general Lemaitre-Friedmann-Robertson-Walker metric, the metric that describes the cosmology of a universe that is isotropic and homogeneous. And the metric is ds squared, or the line element rather, ds squared is equal to minus dt squared in these coordinates, plus the scale factor a of t squared, now times the spatial metric, that is the r squared divided by 1 minus k r squared plus r squared d omega squared. And there we go. This is the Friedmann-Robertson-Walker metric. Those of you taking astro or cosmology may have seen it. Now, what is this parameter k? K is related to the curvature of the spatial sections manifold. If k is equal to 0, you get flat spatial sections. If k is equal to 1, you get spherical spatial sections, positive curvature. And if it's minus 1, you get hyperbolic spatial sections. So this tells you the 3 typical cases that you could have. No matter the value of k would be one of them, obviously. But you know, the observations, current or cosmological observations, tell us that very likely, well, we think with this compatible, what we have observed so far is that k is 0 and we have flat spatial sections. Having flat spatial sections doesn't mean that the spacetime is flat. We still have curvature, all right? We do have a curved spacetime, even though in cosmology, even though the spatial sections may be flat, according to our best knowledge from experiments. Still, it's not, of course, a determined thing that is purely flat. It could be just the radius of curvature is too large, and we just don't know what that scale is. All right, so we have determined that, assuming starting from the most general possible metric, we have determined, applying just the cosmological principle, we are not special, nobody is special, there are no favorite directions. In other words, homogeneity and isotropy, we have determined that the most general metric fitting that has this form. With this parameter k is related to the curvature of the manifold. We can always redefine r to, the important thing for this parameter k is the signature, whether it's 0, positive or negative, where the spatial sections of the spacetime are flat, spherical, hyperbolic. But in any case, this spacetime captures the cosmological principle. And this is called, let me just call it here, LFRW metric. Sometimes only FRW for Friedmann-Robertson-Walker, but it should be Lemaitre-Friedmann-Robertson-Walker. All right, so I'm gonna finish the video here because this exercise was long. So I'm gonna do another video talking about the Friedmann equations. We're gonna actually apply Einstein equations to this particular spacetime and then solve for the evolution of what's gonna happen with the universe. So we're gonna talk about the final fate of the universe. And we're gonna talk about dark energy. We're gonna talk about the cosmological constant. And we're gonna talk about energy conditions that we saw applied to the cosmological constant and what it means. So yeah, come with me to the next video. If I still have some voice, we'll see, because I'm gonna try to record it right next. We'll see what happens with that. And in any case, until I see you, take care.